So today's objective is to go further last class. That means last class we've checked the quality and we've seen in a textual approach and with Avogadro, for example, and Gabedit some informations. And now we want to use the TD information, and I will do some repeat of last year for the electronic density difference, and we'll discuss about pictures, Jablonski diagram, how to draw them. Okay? So just
Yes.
Here in the TD calculation, the atoms does not move anymore. Okay, so if we are at the ground state, that means that if you have a correct optimization of your ground state with all positive frequencies, you are at a global minimum, and you will start to compute the vertical transition. And it's a vertical mono excitation. That means that it's only take into account one electron excitation. Sometimes physically you can have double excitation. That means that instead of a huge excitation of one electron, you can have two small excitations of two electrons. That means that two electrons leaves the fundamental state and to go in a higher state. That is why, for example, the benzene, the simple benzene, is a tricky test. That means that if you try to do some calculations on benzene with TD-DFT, you will be missing some bands. For higher molecules, you have usually less double excitations. So we talk about time dependent because the excited states are not stationary. There are excited states that are not stationary in time, okay? So they depend on time. And it's the general Schrödinger equation, the time-dependent one. Vertical means that you are in the Franck-Condon approximation, and the atoms does not move. When you do UV visible absorption, usually the Franck-Condon approximation is enough. For emission, it depends, okay? But for example, TD-DFT is not the method of choice to assess the potential redox states, for example, for cyclic voltammetry. Cyclic voltammetry is even if you are at 200 milliseconds, it's quite a long time. It gives enough time for the atoms to rearrange, and you don't have exactly the same kind of... And TD-DFT is not made for redox states, for example, to assess what is the ionization potential, for example, usually. Since we use TD-DFT, we also inherit the DFT limitations. In DFT, we have a mono-configurational method, okay? Depending on how we go, we will discuss about it more in detail in the last session. And if you have not chosen a correct functional, for example, for your system or for your problem, or if you have a bad basis set choice, that means, for example, no polarization, no diffusion, you will have this kind of error that exists also in TD-DFT. The selection rule in the UV visible electronic spectroscopy is depends on an electronic transition, and it's a dipolar moment. So we have a selection rule that means that the transition depends on an initial state, psi I, a final state, psi f, and a dipole moment. Okay, that means that there is psi I, that is the electronic function that represents the electron. This is the final function where the excited electron is. If we consider that the electronic reorganization is not too much, but if you want to be more general, psi is the whole wave function of the ground state. Psi f is the whole wave function of the excited states. Okay, and you have an operation that is that you need to create some dipolar moment. If your transition does not create any dipolar moment, you will have no absorption. If your ground state and excited states are totally orthogonal, if there is no overlap between the two, there is no transition. As an illustration, I will use the slides from last year, and I will use, and we will create together the slides for the equivalent slides for the bromobenzaldehyde. For the illustration slide, I use the TTF, and I'm sure that now you have seen the TTF more than once. It's an historical case study. It's still a molecule that is heavily studied in Angers and Rennes, for example. It's the first compound where organic compounds where we observe electronic supraconductivity. That means that here, in a molecule like that, the electrons are quite localized in the atoms, but however there is a p stacking that form a band structure, and since the wave function, the TTF, can lose one or two electrons, if you lose one electron, you can have a half filled band and you have some conductivity. Depending if you have here a redox state, okay, you need an anion, a counter anion, and usually we use the TCNQ, for example, tetracyanoquinone. Beware, when we consider a transition of one electron, the other automatically and let's say super rapidly reorganize, and that means that the wave function of the other electrons can be slightly modified, and this is why when you make an arrow like this, the arrow is correct in the form. That means that if you have a transition that is 100% HOMO to 100% LUMO plus 1, you can draw an arrow, but you don't just look at the energy difference. The energy difference calculated will not be the same, because when you lose the electron here, the electron that stays here is stabilized, and all the other electrons that are in this region feels one electron less. That means that there is less electronic repulsion in this region. However, the excited electron go to a region where there is more electronic repulsion. That means that maybe in the form those electrons, those functions are still correct. However, their energies can be slightly too heavily modified. So this energy difference in an orbital diagram usually is not the value that corresponds to the absorption band. That is why when in spectroscopy you say that you calculate the HOMO and LUMO level with the optical gap, usually it's not a super approximation. It could be quite wrong. What is it has been done more than once, and usually it's correct when you do a series of compounds. That means that if you have a tendency, or if you have some core, okay, pi conjugated core, and you change some substitutions, you will have the tendency. You will see, for example, the HOMO that is decreasing in these three compounds, and you will see that it correlates with the optical gap and with the HOMO energy. The problem is that it's not the real numerical values. Okay, that is why in the Jablonski diagram you should not just put simple vertical lines for the energy levels. You should see the potential energy surface, and it will be helpful to then understand how what happened for the stock shift. Okay, so we'll try to build this one more or less, okay, with the information that we have with the bromobenzaldehyde. I will just present rapidly what is the electronic density difference picture and why is it useful. So we have a selection rule. If we consider that the electrons that are not excited, that means that all the electron minus 1, they keep in the same region. They are, let's say that the electronic reorganization is not too strong. We can just consider that the transition depends on the initial orbital of the electron to the initial orbital, the final orbital of the electron. So for example, if we consider in the let's see a planar version of the TTF, that means that I forced a D2H point group symmetry. The HOMO is in a group B3U, and there is a dipole, and this is in the character tables you will have the dipoles, and in this group it's B1U, B2U, B3U. So you can do the symmetry produce with B3U multiplied by B1U, and you can multiply and find what could be the orbitals that could do a transition. And for example, the LUMO and LUMO plus 6 is an AG. So if you do B3U, B1U, AG, the problem is that you need to have a produce that is AG, and this is not the case. The only ones that do works are LUMO plus 1 and LUMO plus 3. That means that in this molecule, the HOMO-LUMO is a silent transition. It corresponds to a produce, a selection rule that leads to a zero value. So when you do an optical gap with the TTF, you're not calculating the gap HOMO-LUMO, you are calculating the first absorbing excited state, and sometimes it's not the LUMO. So here we have a comparison. So we have the experimental spectra, we have the theoretical spectra. To be more precise, in the calculations, so that's what we've seen last time, we have one energy value for the transition. Here we can consider a Gaussian approximation with, for example, the Gauss-Sum program, and you can consider a Gaussian for each transition, and you will have a first approximation of the thermal effect and Doppler effect and all the effects that exist in the solution when physically you're measuring your spectra, because to have only one energy for one transition, that means that you are in a dilute gas phase without any mobility of the molecules. That means near 0 Kelvin. Okay, so with a Gaussian approximation, you can have a first point of comparison. Here we see a first small band, an intense band. The intense band probably corresponds to this one, and this one to this one. And we don't have anything here. During years, here there were a scientific discussion, we could say battle, between is it the LUMO, is it the first singlet that is silent, or is it a triplet states, or is it a dimer in solution. What is quite funny is that indeed the first singlet with the homolumo that is in principle forbidden, with the temperature you can see it a little bit. It's also there is also a triplet in the same energy region, so it could be also the triplet, and it could be more or less a dimer. So probably it's the sum of everything. So here you can compare. Okay, so here you see that the epsilon are not rigorously correct. However, keep in mind that when you do the epsilon, usually experimentally you are quite sure of your -4 concentration, but are you sure for your if it's 1.-4 or 1.1, 1.6? Okay, and if it's 1.1 or 1.6, you can have like a huge increase in the change in the molar absorptivity. So calculations intensity are not perfect, experimental intensities either. Okay, when you compare the two transitions that are calculated here, the HOMO is a pi orbital. It's a pi between the three double bond of the carbon, and a pi star with the officially non-bonding electrons of the sulfur. So here you have a participation of the non-bonding electrons in the pi conjugated system, and here in the highest in energy orbital, they are in anti-bonding. That is why the HOMO is quite high in energy, and when you lose those electrons, the TTF does not break, and it just adapt. The LUMO +1 is a carbon-carbon pi star with the outer carbons. And the most intense here, the blue transition, is a pi star with the atomic, the central carbon-carbon bond. That's why in the TTF that we also correlate, we found that there is a good correlation between the vibrational energy of the CC double bond near the 1060 wave numbers, and it correlates well with the quantity of TTF plus, the cation form, since in the cation, when you lose here one electron here, you're clearly losing a pi contribution, and you're going to something that is more a single bond, and so you have a shift in the infrared spectra in this band. So let's compare with the first selection rule. That means that we need to have an overlap between the starting, the hole, and the excited electrons. So those are the two wave functions. And if you do the overlap between the two, you try to look at where there is, in both cases, the orbital. That means that here you have no contribution or a really low contribution. So this is 0 multiplied by this, it's 0. So here we have an electron, we have a wave function here also. That means that in the produce you will have it. This overlap is between 0 and 1. And that means here that you have 80% of overlap. Quite huge. When in DFT, it has been shown here with this article that if you are under 30%, you have electrons, the electron in the excited states and the hole are quite separated. And formally in DFT, you may see you lose some predictive power of the DFT. Your error is increasing, and it's not a black or white value. That means that if you have 0.29 or if you have 33, you don't see something that is radically different. That means that if you go beyond 0.3, you will see an error. You should see the error increasing. We have calculated the overlap Tozer parameter for the second transition, or for the first one, the small one, and you see that the overlap here is less, is 0.62. So here we have a higher overlap, higher probability, higher intensity. The intensity of an electronic transition correlates with the probability of transition. If this transition is favorable, if you have an oscillator strength that is higher, you will see a band that is more intense. Okay? So for the first part, the overlap, this transition, we can understand why this transition is more intense by looking at the Tozer overlap, but we can also look at what is happening for the electronic dipole. So in this case, you do the produce. Here, for example, you have white multiplied by blue-white. White and white, it's blue. White-blue is white. So for example, here, if you have something that is minus and minus, that's positive, and minus and plus, that's minus. Okay, blue and white is a sign, it's plus or minus. So here we have, when we have 2 times the same sign, it's plus, it's blue, and when we have a change in sign, it's white. That means that, for example, here, when you have white and white-blue, you change the sign. What you can see is that here we have a molecule that normally is symmetrical. Here we have a symmetry plane, and here another one. And with this transition, you break the symmetry up, down. When in this case, you break the symmetry right, left. And if you count the barycenter of this change, that means that you do the barycenter of the white and barycenter of the blue, you have here a distance that is higher. it's not in the same direction. Here in the zeta direction, here it's a y direction, and the distance here is shorter. That means that the most important electric dipole is created in this transition, where the overlap is higher. Higher overlap, higher electronic transition dipole. That means it's an higher. It's a more intense transition. So we have this kind of information in the text part. If you use GaussSum, you will have the wave number, the wavelength, the oscillator strength. The oscillator strength is this information. That means that here you have something that is the first band, the second here, the first you don't even see it at 450, but at 369 you have something that is quite small, then 0.14, then 0.26. Then again something that is quite small, and then again more important. Then here is you at 230, for example. Okay, so here this is the real information that you have in the TD.log, and GaussSum, for example, or my QChem report or other programs can use a Gaussian approximation to transform this in a spectra. And we've discussed the importance in this case to set a correct width at the half maximum, and usually 3000 wave number, it's okay, but it can be tuned. For example, here the experimental data. The experimental data is a dotted line, and you see a change here, like there is two bands. Is it a fine structure? Is it a vibronic coupling? Or most probably is those two transitions experimentally are a little bit more separated, and the Gaussian approximation is too large here, and you can see the scale, okay, and you see the two electronic states separated. However, this one is hidden here. So you see how much looking at an electronic spectra, experimental one, does not allow for correct rationale. You cannot explain the transition if you don't have more other information. Quantum mechanics, that means, for example, TD-DFT rationale, or someone with a similar compound with some calculations to tell you, okay, the first band is due to this kind of electronic effect, and so on. But now, if you have the TD calculation, you can understand what is happening, and it correlates here in the transition. So, for example, this is not exactly the TTF. It's a derivative of a TTF. The HOMO-LUMO band at almost 100% is 0 in oscillator strength, and the first band, this one, is an HOMO-LUMO plus 1 and HOMO-LUMO plus 2. So here you see that there is two transitions, but in reality there is only one electron that moves. That does not mean that we have one electron that goes to LUMO plus 1 and one electron that goes to LUMO plus 2. No. Here, what the information that you see here is the excited states, the second excited states cannot be described with an electron in LUMO plus 1. When he gets there, there is an electronic reorganization, And to have the correct final state, it needs to mix LUMO plus 1 and LUMO plus 2. That means that to understand the final wave function, you need to do a linear combination of the LUMO plus 1 and LUMO plus 2. Here, for the third band, you need to do a linear combination in the end of LUMO and LUMO plus 2. And to understand that in the starting part, when he moves, the other reorganize, and it is as if the starting electron came from 43% of HOMO minus 1 and 39% of HOMO. And you see that the sum of the two is not equal to 100, so that means that there is minor contribution of other orbital. And for example, for the most intense one, you have 3 transitions to explain one monoexcitation. And this is quite tricky. That means that if you have to print 4 pictures, you have to print, okay, you have some bit of HOMO minus 1, HOMO, and HOMO. That means that you picture this and this. Okay, so the starting electron does not come only from that, it comes also from that. That means that it comes from all the pi system. And it goes to a little bit of the LUMO, a little bit of the LUMO plus 2, and just a little bit of LUMO plus 7. Quite tricky. That is why we will use the electronic density approach. That means that instead of looking at the wave function, we can look at the, okay, I do all my density of the ground state, I calculate all my density of the excited states, and I do excited state density minus ground state density, and the difference is positive where there is an electron density in excess in the excited states. That means where is my excited electron, and negative where we have lost density during the transition. That means in my hole, and where and the atoms who have seen no modification in the electronic density. That means that there are there is electron density of the hole and of the excited electron. This contribution disappear. So here, and you will see something similar in your pictures that I've generated. In the blue surfaces, you have gain an electron, and here in the white grid or white surfaces, you lost electrons. This is the adenine. That means that here, this part is a non-bonding sigma non-bonding of the nitrogen, sigma non-bonding of the nitrogen, sigma non-bonding of the nitrogen. So he lost a little bit of density, a little bit of density, a little bit of density, some of the sigma bonds here, and he gained density here, 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 and here. But not in a, for example, not in this double bond. In the atom region, it is like if you have some anionic character in your carbons, here, here, and here. So you lose some density here, it goes to the pi orbital, and it goes to a non-delocalized orbital. So chemically, this picture, in just one picture, you can understand the process, the electronic transition process, and you can say, oh, okay, that means that this part of the molecule lost density and this part gain, and you can even say if it's a pi star. So for example, a derivative of TTF, we have the HOMO here that is in the TTF part, the LUMO in the triazine part. So here this transition is indeed an HOMO-LUMO transition. So with this kind of transition, you can picture, just looking at the HOMO-LUMO, that you lose density in the HOMO part and you gain in the LUMO part. And you see here that you have orbitals, 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 orbital. So this is your bridge. So when you compare the density, you see in blue where your electron is now. So he is going to the triazine and he comes from the TTF. And you see here that you have a blue and white. That means that you have an electronic reorganization here. Okay. So if you do some quantification, that means you can count here the barycenter. Here it's the barycenter of the excited states electron. Here it's the barycenter of the hole, and you do for example, you measure the distance. So you have the distance of charge transfer. You have the quantity of electron here and the quantity of hole, and you can it's both the same, and it's 80% of the electron. That means that 20% or 19% of the electron stays in the same place. Here you have the charge transfer quantity, and that corresponds to a charge transfer dipolar moment in transition. That is, during the transition you have a high dipolar moment of 20 dB, 21 dB, with an overlap of 0.44. In the case that I've shown you before, instead of a table, you can present here, associated with the transition, the picture of the EDD. And to interpret the chemical phenomena, it's easier. Instead of 4 pictures, you have just one picture, and you can see here, oh, I lose density here, here, and here. Those are my 3 double bonds, carbon-carbon double bond. I lose density also here, 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 and here. Those are my 4 sulfur non-bonding or pi electrons, and they goes to non-bonding sigma electrons. And here you lose density in the middle, and they go to the atoms. That means it's a pi to pi star orbital. So here you have a main contribution of a pi star TTF, and you can compute the dipolar moment that is just weaker, okay? And you can correlate this and understand the chemistry. For example, here you have chiral stereocenters, okay, carbons, and they are not participating in the transition. That means that this transition has no chiral component. That means that you will not see this will not be a strong circular dichroism band. The circular dichroism is the UV visible absorption spectra, but to taking into account a polarized light, and you can have, depending in your chiral form, an interaction that favors or change the absorption between the R and the S, for example. Last example with the quinone based compound, and we have here a quinone with 4 substitution. Here you have an inversion symmetry, when here you have a symmetry plane, more or less. But that means that you don't have exactly the same 3D component, but you have the same chemistry. You have here in the higher region two similar forms. Here we have a band that is quite similar, and here at 550 you have one band for the meta substituted, that means this one, when in the black you don't have anything, or really a weak one. And when you do the computation, indeed you find a transition here when there is none here. By the way, if you compare here, you have a band that is anticipated at 550. I think the calculations is here, and this is the experimental data, because my oscillator strength is at 660. But here you have a difference. Here you have 100 nanometer of difference. But if you compare in electron volt, what is the energy of 650, for example, nanometer and 550? Those 100 nanometer, it's a little bit above 0.3 electron volt. If you compare here in this region a difference of 30 nanometer, it also corresponds to 0.3 electron volt. That means that here, since 300 nanometer is much more energy, it is logical to see less difference between experimental and theoretical. Whereas in the low energy region, since the energy difference can be of 0.3, it can induce a difference in nanometers that is quite huge. That is why usually I prefer, when I want to show some, to compare experimental and theoretical, to work in wave numbers, in centimeter minus 1, because it's linear in energy. But since with chemists it's more intuitive, or you have there is an habit of working with wave numbers, wavelengths, so we publish in wavelengths. So here we can look at the first excited state. In the meta part, there is a small absorption, and this is what we observe here. And what we see is that the thiophene lose density, those two double bonds lose density, and you populate the pi star of the CO bonds. So the acceptor part is the carbonyl one, and you populate the pi star. You don't populate the pi because it's already occupied, and you see that the electron density is not between the carbon and the oxygen, it's on the oxygen and on the carbon. So this is the pi star. And you populate a little bit the double bond here. So you give the electrons here, and it's loose from here and here. Physically, the first excited state in the para substituted is the same physical process. However, since you have something that is symmetrical, you will see here that the overlap is the same, it's the dipolar moment that is different. So let's look at this picture again. Here, the center of mass of this excited electron is in the middle. Here, you see that the white, the hole is more centered here, around here. So you have a dipolar moment in this direction. When here, since you have an inversion point, you have the center of mass of the hole and the center of mass of the excited electron at the center of the kinon. That means that the electronic dipole transition of this transition is 0, and the probability is 0. So the white, the black curve is 0 at a low energy. Let's do the same with the bromobenzaldehyde. Okay, so for those we have the report, you already have some pictures. The other, and there is no obligation, but with the others you need to use Avogadro, for example, to get the HOMO pictures, or GabEdit, or Gauss-View, as you wish. So let's copy. Let's insert the pictures of the of this molecule. Okay. So when you do some calculations, I've recommended to you that you look at the orbital, the molecule in 3D, just to check that if it corresponds to something that you in the geometry that seems to be quite logical. You need to also explain the computational details. So when you will present your results, you need a slide, okay, or you need to put somewhere what are the computational details. So in the report they are here, but you can find them in the input, in the output, somewhere. Here we have a function that is a PB1 PBE. Also called PB0. It's an hybrid functional, okay, with 20% of Hartree-Fock. So it's similar to the B3LEAP having 33%. So there is a little less of Hartree-Fock. It's more efficient for excited states for pi conjugated systems. If you have a large charge transfer, maybe PB0 is not the best. If you have intermolecular interactions, it's not the best. So here you have the number of basis set function, okay? So you need to check really what is the name of your basis set in your input or output. So if I go if you open one of your log file, you should see in the optimization these numbers, okay? So those are the name of your basis set. So we've done some TD-DFT with a functional and a basis set, okay? you need to put those, and you need to be sure of what are those. Just as a reminder, in your Schrödinger equation, your Hamiltonian is not the full Hamiltonian, the exact Hamiltonian, because we don't have the electronic interactions terms exactly. So we use an approximation, and it can be in DFT with the functional. And we also do an approximation of the wave function as a linear combination of atomic orbital. Those are linear combinations of Gaussian orbitals almost for all cases. If you do calculation with ADF, another program, sometimes they directly use a Slater orbital, but many times it's a Gaussian function. And here it's clear, the G here tells you that it's a Gaussian function. Triple zeta, so quite huge. 2D orbitals, two sets of d orbitals for all atoms, and one set of f orbital for all heavy atoms. That means everything that is not hydrogen, so it's quite huge. And two sets of p orbitals and d orbital, and one set of d orbital for the hydrogen, so it's a huge basis set. And we add some diffusion, so this is quite a large basis set. Here we have closed shell calculation. Okay, that means that all orbitals are occupied by two orbitals or zero. Default integration grid, it's ultra fine now. There is no solvent. Okay, and we have a convergence in density that is -8, for example, -6 on the energy. We have the thresholds and the value obtained in the convergence. So we can see here that in the forces we are under, and in the displacement also. That means that we converged our ground state on 4 criteria. We have calculated 15 excited singlet states, 15 triplet states. We've done a frequency calculations at room temperature. We have the total energy. Okay, we know that the HOMO is the orbital 45. We have the HOMO energies, LUMO energies, okay, LUMO plus 1 and HOMO minus 1. And we have the here calculated monoelectronic excitation. So it's the same as the table that you can see, for example, in GOSU. We have the symmetry, we have the wavelength, wave number, oscillator strength. R, this column is for the circular dichroism. So here it's not a chiral compound. We have a slight helicoidal shift because it's not fully planar, but the values are really small. You have the lambda parameters, the distance of charge transfer, quantity of charge transfer. And you have some frequency calculations with the 0-point energy, total thermal energy, enthalpy, and free energy, and the entropic contribution. So this information is present in your frec.log. The most intense molecular vibrations in wave number, this is also a result that comes from the frec.log. Beware that the values here are not modified. Usually, if you want to compare with the experimental data, you need to do a multiplication. Okay. This is the other monoelectronic excitation with the triplet states. In this case, when you calculate the triplet by symmetry, because you change the spin state, the oscillator strength is 0 always. Always 0. That means that here we have only 0 orbitals. Okay. So let's start with that. We have, so okay, up, I put this here. No, not what I wanted. I want to duplicate the diapositive. No, it's a picture. Yep. Maybe no. So here we have our ground state. Since we have the TD-DFT in our table, okay, but you can also find this energy directly in the TD. I know that maybe we'll work in wave number. Yeah, maybe. Okay, so here we have let's see. Okay. $30,000. So here you have a first singlet. Okay, there is no absorption. F equals 0, and it's 30K, 30,000 wave number. And you have a second excited state with a huge oscillator strength, okay, at 39,000 wave number. So I will write this ES1 or So here we have first excited states, second excited states, okay? And the third is almost with no absorption, okay? And we have the triplet states. In the absorption, if you have computed those absorption, okay? So here, for example, you have the table for the triplets, and you can see that the first triplet is at 25,000 wave number. That means it's 5,000 less than the ES1. But there is also the second triplet state that is at 25. And then we have 33 and 35 and 38. So until this level, we have like 5 triplet states. 2 that are below here, and 2 and 3 that are between the two. So change color in green. Let's do the triplet in green. $33. 35. 37. In T1, you will always have an oscillator strength that is 0. Do you recall how much vibrational energy we say we could expect to have? How much in energy difference we need to have to forget about a vibrational relaxation? That means that, for example, between two states, we will say, oh, there is no vibrational relaxation because the energy difference is higher than. What is the value of this energy difference that we could use to say if there is or not vibrational relaxation? Nobody? I'm alone.
No.
Do you think that you can have a vibrational relaxation between the excited state 1 and the ground state?
It doesn't seem to be a forbidden transition.
We don't have this information. We can say if electronically you can have a transition. Okay, so the oscillator strength, for example, here is 0. That does not mean that you will have a vibrational energy relaxation. A vibrational relaxation. This is the electronic relaxation. That means that you absorb light or you emit light. To know if you have a relaxation, you need to compute the frequencies, and just if I so this is the first vibrational level, zero point energy level, and then you will have several transitions that are possible, and you will form a series of vibrational transition. And my question is, how high in energy will I continue to draw bands?
For every vibrational and rotational states, there will be one level.
There can be more than one. For example, if you consider an harmonic, so if your vibration is super intense, you have a probability of an harmonic. Okay, okay, but up until how high in energy? That means that, for example, here my lines are too far apart. If you have a transition, it's for example 1000 centimeter minus 1, so it's really something that is more narrow and they are nearer. Okay, but how high can I go?
Not higher than the curve extremities on the fundamental states.
This could be it's a good answer. However, here I don't have this information.
Oh.
So here I've just put my two lines because it was quite practical, but I don't have my Morse potential.
So you are expecting
a value.
One value, okay.
Or an order. At least how much?
I guess it would be, I can't give you one value, but maybe a multiple of the transition state, of the energy of the transition states.
No, it's no. When you have the you have an overall estimation of the vibrational energy in your infrared spectroscopy. So you know that, for example, when you have a CH bond, you have like vibrational energy of 3000. Here, in this molecule, you will have a double bond here in the CO, so it's 1700 around. You have several CH bonds. Okay, you have a CBr, and you have out of plane here, but here you have at least 4000 wave numbers of vibrational energy with discrete levels. If you repeat with the first harmonics, for example, here you have like a first harmonic that is at 3005, but you picture some combination, but you will not get further 8000 wave number. So here, if you have 8000 wave numbers, you have harmonics of vibrational energy, and they are quite low in probability. So here, if you stop at 8000, you don't reach the 29 or 30,000. Do you understand? That means that here, for example, here, if you have an energy difference between ES1 and ES2 of 10,000, it starts to be quite a lot to go directly from ES2 to ES1. But you can see here in this diagram that between ES2 and ES1 there is ET5, ET4, ET3. And you've been told that you can have intersystem crossing between singlet and triplet states if the vibrational levels correspond. And it's not totally correct. When you have the excited state 2, your electron is excited at some place in the molecule. So let's see what is it. So if we add the EDD, that means that I will insert the electronic densities. S1. Not so big, please. Three. Okay. Then insert ES2. Three. Okay. Insert ET. ET1. Two. Okay, so ES1, you lose an electron density in the non-bonding region of the oxygen here of the carbonyl that is along the sigma plane, and you gain electron in the pi orbital here. That means that you lose some non-bonding oxygen here to the pi here until this part. So it's a sigma non-bonding to pi. The overlap is really weak, oscillator strength 0. Whereas here you lose electronic density of the bromine and some of the pi region of the benzene that reorganize to 2 atoms of the of the benzene and the pi star of the carbonyl. So here you have something that is more the bromine gives electrons to the pi star of the carbonyl. The bromine acts as the donor and the carbonyl as the acceptor, and we see here the role of the bridge. Okay, and here the overlap will be better because everything is in pi symmetry, and you have here some electrons. You see a reorganization in the pi star, in the pi conjugated electron, so you have an overlap. And you can compare here in your table that here lambda is 0.44, so weaker, and here it's higher in lambda. And the mu CT is bigger like this. Okay, so we have here an absorbing excited states that are that we understand well. You can understand it again looking at the orbitals, and maybe here you see that this transition is mainly at 89% is the HOMO-LUMO. So if you told me that, okay, this one is the HOMO-LUMO, so this is the second state, the second excited state, and I don't have the EDD, I can look at the orbitals. So I have the HOMO. The HOMO is in the pi in the pi region of the benzene, and quite a lot in the bromine, and there is almost nothing in the carbonyl. And when I look at the LUMO, there is nothing anymore in the bromine. That means that the electron here goes to the benzene and to the carbon of the carbonyl when there were nothing here. So clearly here you gain electron, you lose electrons. Okay, so if you do this picture squared, this picture squared minus this picture squared, you have something that is this picture. Just to remark something, that's the HOMO-LUMO transition is not the first one. Here, the first transition is the HOMO-1 LUMO. That means that when the electron leaves the HOMO-1, it goes to a new orbital, and the reorganization of the other electrons stabilize this excitation more than the transition of the HOMO-LUMO. So when you have an HOMO-LUMO, you stabilize less the other electrons, and that is why the HOMO-LUMO can be higher in energy than the HOMO-1 LUMO. Look at the excited states. To see if you can pass and lose energy and change from one excited state to another excited state, you need to see if the excited electron is at the same place, and if you have a vibration in this region that is quite intense and that can couple. To do a vibrational de-excitation, you need to couple the excited electrons and a vibrational. And a vibration that is quite intense in this region. Here we have the double bond CO. It's super intense in the vibration in the ER spectra. You have outer plane angular deformation of the benzene, and you have probably the CBr, but here the most important bonds concern the aldehyde. That means that, for example, here ES2 and ET5, I think they will not match or not great, because the excited electron, if you go from ES2 to ET5, you will get the excited electron move in this region. Whereas if you go directly to ET4 and ET5, your excited electrons still here is in this region, and doing a CO vibration, you will lose packets of energies of 1700, and you can go from here to here, and then from ET3 maybe to ES1. Yeah, well, you have here the excited electrons, you have some electrons here. They could go directly maybe from this one to this one. However, that means that the hole change drastically. The hole that is in the bromine moves to the sigma star. It's not super favorable. Okay? When you look at it, you can see here that your electronic transition can goes up to your ET1 with ET4, ET3, and maybe directly here, depending. But you can see that there is a huge resemblance between the two. Likelihood. Okay? ES2 and ET1 are the same. That means that, you see, ET5 electronically does not match with ES2. So when you have intersystem crossing, you need not only to have a vibronic coupling, but you need to have an electronic match, and you need to look at the excited electron. Where is it? Is there any intense vibration that can couple with your excited electron to help lose some energy and to go to a similar or a parent excited state, and to still lose energy with this kind of vibration? So if we open again the Bolton, where is it? So in this article, okay, so here those are solutions and solid states. Okay, so absorbance, expected absorbance in solution 350, and we have something that is lower in energy. Okay, officially 330, it's a non-absorbing state. That means that we have quite a huge error in energy for ES2. keep in mind that here we don't have the alkene chains and we don't have the oxygen, and it's a solution, and we don't have we have a purely gas phase. Okay, so it's not quite correct. We don't have the intensity. Maybe the intensity is quite low. We don't know. It's normalized. And we have only one band. So here I cannot say if this is this band that is weakly observed experimentally, or if this is this band and I say and we have maybe a calculation that is not fully in agreement for a problem of substitution and so on. So here, if you consider a Gaussian approximation, the zero transition here is silent, and the first band is at 260. So that means that there is quite a lot of energy difference. If it occurs for you, you need to discuss the reasons why. We have first possibility, this chain is not electronically silent. That means that this chain change the electronic properties, change the energy of the transition, and maybe change also the symmetry of this first band, and now the oscillator strength is not 0 anymore, but you have something that is around 350, and now it's correct. So if we want to go further, I will change the chain and go again to do my calculations. If you look at the energy of the triplet, it's 400, and we are expecting a solution emission at between 400 and 450. So could be possible. However, since I do not fully understand what is going on in the absorption, it's quite tricky to say that, oh, the absorption is not correct, but the emission is correct. And let's finish with the emission. And this is one of the most important errors that you've done, or that the previous years have done. When you calculate the emission, okay. When you calculate the emission, and when you do the Gauss-Sum, for example, with the OPT ES1, you have a problem. Gauss-Sum is not made for that. There is a huge problem. Gauss-Sum is made, is waiting for a file where there is only one geometry, and for example, he will see 15 states with this energy, but also 50 states with this energy, 50 states with this energy, and you will see a lot of electronic states. He will aggregate everything. So there is a huge problem here. And two, when you do a PTES1, you have still 15 states, but they are calculated. If you recall, what we do is that when we want to optimize ES1, we do a calculation of the ground state and we try to minimize the energy difference between the two. So we are looking here where this is minimum. So you will have a change in energy. There are still absorption. That means that he's not doing an emission calculation. He is doing a calculation of the a new absorption where the ES1 is at the lowest energy. And in his calculation, he's still calculating the energy to go here, here, and there. He needs the other informations also. So that means that here in OPT-ES1, the only values that are interesting for us are the energy of the state that you are calculating. So when you do this, the new state ES1 is at 405. That means that here you start at 335 and you go to 405. That means that this here blue should be much lower in energy. You need to do no, it will not be correct. But here the blue, the violet one is lower. It should be here, and this curve should be there. That means that you have an energy surface of your excited state that is more drastic. You have an energy change that is quite more drastic. That means that between the absorption and the emission, you lose quite a lot of energy. And you are at 400. And 400 is more or less what we have seen in the publication here. So in the publication, in the solution emission at 400, it could be the first singlet with a weak emission. And let's recall that in solution, he says that it's a fluorescence. And we need to optimize the triplet to see if the triplet goes really near the ground state, that maybe, probably, there is a vibrational relaxation and you don't have any emission. Okay, so I'm just working in this diagram right now. And to understand this one, I should do the dimer. Okay? So, ground state calculation, frequency calculation, TD-DFT calculation of the singlet, of the triplet, but I think that for you, no one has asked the triplets. So you have the vertical transition, and some of you have the optimized excited states. You can compute the energy evolution, and you can see what is the difference here in energy to understand the stock shift, the emission property, and so on. Okay, so optimization frequency for the ground state, TD for the vertical absorption, OPT-ES1 for the vertical absorption, but with an optimized excited state. That means it corresponds to the emission. So we make a break and we start to discuss about your results and to discuss of what we can do with your files, what you can do, and so on. Okay, and you can work in groups also. For those who have already the information, you can work in groups and you can comment. Okay, let's do a 10-minute break.